Hello, today I'll be coding a tetrahedron as a regular triangular pyramid. So let's get started by creating the triangular faces. In order to do this, we're going to have a mixin, a regular polygon mixin. So a regular polygon is one that has all edges equal and all angles equal. So here we're going to take the number of vertices, which is equal to the number of edges, and the circumradius. And we're going to set some defaults here. The number of vertices is going to be the one we set, or 3. And the circumradius is going to be the default, let's say it's going to be 400, something like that. Now, if you don't know what a circumradius is, it's the radius of this big circle on which all vertices of the polygon are situated. So in this case, we have a triangle, but we can also have a square, pentagon, hexagon, heptagon, octagon, and so on. So going back here, we're going to compute a base angle. So the base angle is the angle corresponding to one edge. So if we have 3 equal edges, then each one is going to have an equal angle that corresponds to it. So since we have 360 degrees around the circle, this means that to an edge, for a polygon with n edges, we're going to have an angle corresponding to this edge that's 360 over the number of edges. So 360, it's 2 pi over n. And now we're going to have an array of vertex coordinates. And this is just an empty array at first. Now we're going to have a loop. So I from 0 all the way up to n, and we increment this I index. So this is the index of the current vertex, and we're going to have the current angle, and this current angle is I times the base angle, and you can see it here. No, actually here. For the first vertex, vertex 0, we have 0 times the base angle, 1 times the base angle, 1 times the base angle. And it's the exact same thing if we have more vertices. Same thing. Okay, so we have the current angle, and now we're going to compute the coordinates. So the coordinates, we get them using this formula right here. So we have the coordinates of a point in a plane. They're relative from to the distance from the origin, and the angle formed by this radial line with the x-axis. So we're going to use these formulas. The distance is the circumradius, and the angle is the current angle, cosine. And it's pretty much the same for the y-coordinate, except this is sine. And finally, within the loop, we also add to the array of vertex coordinates. So push this pair of coordinates, x, y. Now here, we're going to have an SVG and a polygon. Now, the size of this SVG should be enough to fit the circumcircle. So that means it should be the diameter of this circle. So we're going to compute this diameter, which is going to be 2 times the circumradius. So we're going to have view box equals, and we have the x and y offsets, and then we have the dimensions for the width and for the height. Both width and height are equal to that diameter. And since we want the 0, 0 point to be right in the middle, the coordinates of the top left corner are minus half the dimensions. So minus the circumradius. And now we have points here. And this is the array of vertex coordinates. And we need to join it by space. So this is pretty much it. Also need to join stuff there. Okay. Now, in order for this to produce something, we need to call the mixin. Okay, this works. Now let's say we want the first vertex to point up. So we want the first vertex to be at 3 o'clock, to be at 12 o'clock here, not at 3 o'clock. So we need to go from 3 o'clock to 12 o'clock. The difference is 90 degrees. Is that plus or minus? So if we go from 12 o'clock to 3 o'clock, that's clockwise, and that's the positive direction. But going from 3 o'clock to 12 o'clock, that's minus. So that's going to be an offset of minus 90 degrees. So when we set the offset here, we're going to set offset, and same, we're going to set some default values, or minus 90 degrees, which is half of pi. Okay, so here we're going to add the offset, and now our triangle points up. Good. Now let's see how it looks with the circumcircle. So we create a circle of radius, the circumradius. Now we're not going to see anything unless we do a few things here. So first of all, we're going to set a background on the SVG, and that's going to be gold. We're going to set a fill. This fill gets inherited. Fill strokes we set on the SVG get inherited to everything in the SVG. So fill none, and we're going to have stroke current color. And now we can see it. We have the triangle, we have the circumcircle, everything looks perfect. Okay, however, if you want a thicker stroke, so stroke width, for example, let's say 0.3 times the circumradius. Let's get rid of this. This doesn't look right anymore, and this is because the stroke extends both inside and outside the shape. So in order to see this better, this is the dashed line here, is the limit of the shape. With this tan color, whatever you want to call it, that's the stroke width, and the stroke extends both inside and outside that dashed line. So here is the point that should be right on the edge, and the distance from this point to Q is by how much it goes outside. And this point is right in the middle of PQ. Okay, so if we can compute PQ, then we can compute this distance, and we know how much to subtract from the circumradius and get the actual radius. So what we're going to do is here we're going to have an actual radius. This one is going to be RC minus 0.5 times something we don't know yet. And we're going to use this actual radius here. Okay, now let's see that value. How much is this PQ? So in this PQR triangle, we have that this angle R, this is a right angle. So you have a right triangle. PR is the stroke width. This alpha angle is half this the angle at the vertex, which we can compute. So we have that the sine of alpha, which is half the angle of the vertex, is PR over PQ. So if we get PQ, this is PR over the sine of half the vertex angle. So PR being the stroke width, so we have the stroke width over the sine half the vertex angle. Now, how much is the vertex angle? Well, the sum of angles in a triangle is 180 degrees. But what about a generic polygon? Well, for a square, we can split it into two triangles. And as you can see, the sum of angles is additive, because the sum of angles in this triangle is this angle, small angle right here, plus this big angle, which is the angle of the square, plus this small angle right here. This is the sum of angles in triangle 1. The sum of angles in triangle 2 is this small angle here, angle of the square, this small angle here. Now, if we add up the two sums, we get the sum of angles in the square. The same thing for a pentagon. We can split it into three triangles, sorry. And the sum of angles of the pentagon is 3 times the sum of angles in a triangle. And the same thing for a hexagon. We can split it into 4 squares. So in general, the sum of angles in a polygon of n vertices and n edges is n minus 2 times 180. And if this polygon is regular, meaning that all its angles are equal, a vertex angle is going to be this product between n minus 2 and 180 over the number of vertices. So this is how we can compute the vertex angle. So let's do it. The vertex angle is, as I said, n minus 2 times 180, which is pi, over n. And now that we have this, we should get the correct result. Since we didn't, something must be wrong. Oh, okay, stroke width. We need to set a stroke width. And here we have the default, and by default it's 0.1 times the circumradius. It can be anything else by default. And here we need to set the stroke width to that value. And this works for any polygon. It doesn't matter, we can have a pentagon here, and it works just as well. So now let's switch back to triangle, and we have a bit more than this here. We're going to have a seam, and one more thing we're going to do here is replace this with a symbol. Put it inside this SVG. Here we're going to have a 3D shape, and within it we're going to have some 2D SVG faces, and here we're going to have use elements that are going to reference our symbol. But for now we don't have an ID to reference, so we're going to need to fix that. So ID, and here we're going to have pretty much the same thing, sim. Okay, now one more thing that we're going to need to set here. We're going to need to set these values. So we're going to have three, and this is going to be 400. Doesn't really matter. Okay, now that we've done this, here we're going to use only the SVGs that are 2D faces. Okay, so now that we've done this, let's move on to styling this whole thing. So we're going to have scene, and we're going to give it background purple just so that we can see it, and we're going to give it some dimensions. So we're going to have scene width. Let's say we make it cover the whole viewport. So now we're going to set some dimensions, actual dimensions. And one more thing, to get rid of the scroll bars, we're going to do margin 0. Okay. Now, one more thing we're going to do here, not exactly here, make everything position absolutely. And here we're also going to need to set position relative. And we're going to need to set the dimensions of this SVG to something that's a percentage of the smallest scene dimension. and we don't know which the smallest scene dimension is. So we're going to have here something like a factor. Let's call it k. So this is going to be a k factor, and let's say it's going to be 0.85. And here we're going to compute the dimensions of this SVG, and these dimensions are the diameter of the circumcircle of this triangle. So this is going to be a calc that k times scene width, and we're going to have a maximum value, and this is going to be the scene height. Now when I set the dimensions here, I'm going to have something similar for the height. And now I'm going to take this and use the max values. So this is max everywhere. And as you can see, now this SVG square is 0.85 of the width, but if the height becomes smaller than the width, then it's 0.85 the height. This is really useful, but it also means that we don't know exactly what the dimensions of our SVG are. So if we need to reposition this somehow relative to its own dimensions, then we need to use percent values. So the diameter of the circumcircle is 100%. This means that the circumradius is going to be half of that, so 50%. So this is what we have. And if we want the whole 3D shape to be right in the middle, that's top 50%, left 50%. And this is right in the middle because this 3D shape is a 0 by 0 element, but the 2D shapes are not 0 by 0 anymore. So we need to translate them by half their dimension. Translate them up and left by half their dimensions. So transform, translate, that's minus 50%, minus 50%. So this brings everything right in the middle. Now let's get rid of that background. And we're going to do a few more things here. We're going to set a perspective so that things look 3D. And we're also going to set the perspective origin, which is going to be 50%, let's say something like 43%. That should work. And one more thing, we're going to need to have more of these. So we're going to have a number of faces for the tetrahedron. So that's going to be 4, obviously. So we're going to have a loop here. Oh, sorry. And here we're going to indent these. Now here we're going to keep adding to this transform. Now as you can see, the lateral faces are rotated such that their bottom edge is on one of the edges of the base polygon. So this means that we pretty much need to rotate them as we've rotated the points for the vertices. So we're going to have rotate y, and we're going to use a custom property here, which is going to be half a turn by default. Okay, now this should work. And one more thing we need to set here, the number of vertices in a triangle is 3. We're also going to compute the base angle, and this is 360 degrees over the number of edges, which is equal to the number of vertices. Now the rotation angle for the lateral faces is going to be I times the base angle. So we're going to have a loop here. So for I from 0 to how many lateral faces we have, which is equal to the number of edges in a triangle, because a triangle is the base. So here we're going to have nth child I plus 1 so it's I times the base angle. And yay, they're oriented differently. Now, next thing that we need to do is they need to be at an incline. And we don't already know that, but they need to be at an angle with the vertical. Right now, they're all vertical. So they need to be at an angle with the vertical. So that's a rotation around the x-axis. So that's rotate x. And 0 degrees for now. Next, we'd have a translation forward from the point where they are. So that would be a translation along the z-axis, but we can't do that. And this is explained in this article, which is going to be linked from the description. But the deal is we can't have percent values inside a translate along the z-axis. So we need to emulate it with another chain of transforms. So translating this forward should be as simple as translate z something. But if we need to use percentages, we can't use percentages inside translate z. And this is not a bug. It's explained in the article. Go look at the article. So the way we can emulate this with an equivalent transform chain is rotate by 90 degrees along the x-axis. This brings the y-axis where the z-axis used to be. So this rotates the whole element and its local system of coordinates such that its y-axis doesn't point down anymore. It points forward out of the screen towards you. That's the rotate 90 degrees. Then it's translated along the y-axis, which now goes out of the screen forward towards you. And it's brought in the right position, but it needs to be rotated again so that it's vertical again, because rotated by 90 degrees, it's horizontal. So we need to do something similar here. So we're going to have rotate x 90 degrees, and then we're going to have translate y some value, let's say 30 degrees. It's not going to be 30 degrees. We're going to give it the right value at a certain point. And then we're going to have minus 90 degrees. Now, this is starting to look like something. But we need to compute that angle so that we get the incline and everything else. Now, one thing we should note here is that we have rotate x, rotate x. We can combine these two and do something like this. And for the base face, last child, we're going to want that ax to be 0 degrees because we don't have that first ax rotation. And this is starting to look something like a tetrahedron, but we're not there yet. What we need is the angle of the incline, ax, for the lateral faces. Now this is the angle between a lateral face and the vertical. So that's MDO angle. Now in the MDO base, this triangle, this is a right triangle because DO base is the height of the triangle and this is perpendicular onto the base. And being perpendicular onto the base, it's perpendicular onto any line in the base. And furthermore, it's perpendicular right on the center of mass. So if we have, consider that this is the base, the height falls right there in the center of these two circles, which is also the center of mass of our triangle. So this means that O base M, this is the in radius. This is the in radius, so that's the radius of that small circle, which we can compute if we know the circumradius. So let's see how I can compute that in radius. Here in this triangle, this is a right triangle, OMV. In this right triangle, OM is the in radius, OV is the circumradius, MOV, this is half the base angle, which we know. So cosine of the base angle, of half the base angle, sorry, is the in radius over the circumradius. So the in radius is going to be the circumradius times cosine of half the base angle. So this is how I get the in radius. So let's compute here the in radius. This is going to be the circumradius times cosine of half the base angle. Now we need to compute the height of the triangle, because in this triangle DMO base, DM is the height of the DAB triangle. Now in this sort of regular triangle, the height is the circumradius plus the in radius. So this is my height. So the height in this triangle is the in radius plus the circumradius. Okay, now in this right triangle DO base M, we know the hypotenuse DM and the O base M segment. This means that the cosine of this angle right here between the two faces, the DMO base angle, the cosine of this angle is the in radius of a face over the height of a face. So if we take the arc function, we can get the angle. So the dihedral angle is the inverse, the radius, the in radius over the height. And this gives us a value in radians, so we need to convert it to degrees. So we multiply it by 180 and divide it by pi. So we now have the angle between two faces. And this angle between the vertical and the face is 90 degrees minus this angle there from this right triangle, DMO base. So our angle is going to be 90 degrees plus 90 degrees minus that dihedral angle. And this can be written more simply as 180 degrees. So this is the incline that we have. Okay, next we need the distance for this translation. This is the in radius of the tetrahedron itself. And this is going to be the perpendicular from this point O onto the DAB plane. And this perpendicular is going to fall right in the center of mass of this triangle. So the perpendicular is going to fall right in the center of mass. So if the perpendicular is OP, then PD is going to be the circumradius of this face, which we already know. And we already know the PDO angle because it's 90 degrees minus the dihedral angle. And given that the OPD angle is 90 degree angle, this means that the POD angle is equal to the dihedral angle. So this means that the tangent of the POD angle, which is the dihedral angle, is the DP edge, which is the circumradius of a face, over the OP edge, which is the in radius of the tetrahedron, which we want to compute. So this in radius that we want is going to be the circumradius of the face over the tangent of the dihedral angle. So we got our result, and now we can rotate it, animate it. Animation, rotation, 4 seconds, linear, infinite, and we can collapse this, and then we're going to have keyframes rotation, and this is going to be to transform, rotate Y, 1 turn. And one more thing that's missing, we need to set transform style, preserve 3D, so that the faces don't get flattened into the plane of their parent, the 3D shape. And we can also change the color of the lines, gold, something, and it doesn't matter. And one more thing I want to show you, you don't necessarily need to have something like this. You can have something like 30 ems, or you can have something like calc, something like this. It doesn't really matter. This is always going to be relative to the size of the smallest dimension of the scene, no matter what the dimensions of the scene are. So this is the really cool thing about this method, that it's very, very flexible. So this is it for today. You can find the CodePen link to the finished demo and the links to all the other resources in the description below. And if you have any questions, you can drop them in the comments or send them on Twitter. I hope you've enjoyed this video, and if you did and wish to see more videos from me in the future, please consider supporting me in one of the ways explained in the description below. With a donation, by getting me something off my Amazon wishlist, or at least by sharing this video to show the world what can be done with CSS these days, because it's pretty cool. In any event, thank you for watching, and until next time.